Okay, so we're going to start off, we're going to say if x squared equals 2, then x is not rational. Proof. So what we do here is we're going to do a proof by contradiction. We're going to say assume x is rational. And we need to have a good definition of rational in our minds. So if we assume that x is rational, this means that x can be written as the division of two integers. So the rational numbers, this set, as I'm defining right here, is a over b such that a and b are both natural numbers, okay, are natural numbers. Okay, are in the natural number set. So the natural numbers look like this, the regular counting numbers. 1, 2, 3, and then off into infinity. And again, if we have it that we're assuming that x is rational, what that means is that x can be written as the division of two natural numbers. Now, if, again, two natural numbers, so what is rational? Again, let's just make sure we see that with p and q, both natural. Both natural numbers. And we're going to say something else. So now, before we say what we want to say over here, let's just make sure we understand rational. So a rational number is any number that can be written as the division of two natural numbers. So like 2 over 3, 5 over 4, right? This is a natural number. 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 The division of any natural number. So 2 over 4 is a natural number. Now, I want to say, and x is in simplest terms, and we need to understand what this means. Now, any fraction, right? So let's look at these fractions. 2 over 3. 2 over 3 is in simplest terms because 2 and 3 don't share any factors. 5 over 4 is in simplest terms because 5 and 4 don't share any factors. But 2 over 4, they both share a factor of 2, so I can divide by 2, and I'll get 1 over 2, and now I have it so that way this is in simplest form. So these are in simplest form, where you don't share any factors. And we should believe that if I have it that x is rational, then it must admit a simplest term expression or simplest form expression, right? With p and q not sharing any factors. And we need to now see that if x is in simplest terms, or in simplest form, then this implies p and q are both not even. And that's where we sort of want to begin. We need to believe that p and q, as long as it is that this fraction is in simplest terms, simplest forms, then p and q can't both be even. Because if they are, right, then you can reduce it, right? So this is two evens, right? You know that then you could write it as 501 over 350. And now they're both not even. 501 is odd. And this might not be in simplest form, but at least they're both, if it's guaranteed that if it is in simplest form, then they don't share any factors, the numerator and the denominator. P and Q do not share any factors. So you know that they're both not even, because if they are both even, then they'll share 2 as a factor. With this, okay, we begin then saying that we know that x squared equals 2. That's our hypothesis. So I have x squared is equal to 2, but I'm assuming that x is rational, and p and q don't share any factors, and I just substitute p over q for x, and then this leads me to this following algebra. And I get p squared equals 2q squared. Now, this means that now I have this equation being true with P and Q, again, natural numbers, and they don't share any factors. So then in particular, they both can't be even. Okay? So now let's see what we have from this equation. Well, if we look, 2 times Q squared. So Q is just some natural number. So a natural number times 2 is guaranteed to be even. And then I'm going to get that P squared is equal to some even. But this immediately implies, and you should convince yourself, that then P is even. And if P is even, that means that P is the multiple of some integer, or some natural number, I should say. So P is then equal to 2 times M for some natural number. And if P is equal to if P is a multiple of 2, then I go back to this equation again, and I say, well, P squared is equal to 2Q squared. I just rewrote it. But instead of writing P now, I know that P is a multiple of 2. So I write 2M squared in substitution for P is equal to 2Q squared. But then this is 4M squared is equal to 2Q squared. I divide by 2. I'm going to get 2M squared is equal to Q squared when I divide by 2. So I'm going to divide by 2 on both sides. This cancels. I'm left with Q squared, which is a natural number. 4 divided by 2 is 2, so it's just 2M squared, which is also a natural number. And now this implies that this side must be even, because this is 2 times some natural number is equal to Q squared. But then if Q squared is even, then Q is even. And this is your contradiction, because we started off saying that P and Q are both not even. But I have here that I concluded that P is even in this one, and now I concluded that Q is even, and that cannot occur, which means that my assumption is false and X is not rational.